Welcome to our Algebra 2 Semester 1 study guide, a review of the entire semester, all in one go. Let's do this. Number 1 gives us a table of values and asks us 4 or 5 questions, something like that, starting with the domain and range of the relation shown in the table. So domain is x values and range is y values, and when they give us a table like this, we are basically making a list of those values. I am a little worried I'm going to run out of room here, so I'm going to just hope for the best. So our domain is 4, 5, 3, and 10, and you'll typically see squiggly brackets around this showing that it's a set of numbers. You'll also typically see them put it in numerical order from least to greatest, because it's just nicer mathematically. Our range, same thing with the squiggly brackets, but our y values. So -2, 0, and 2. And you don't need to put 0 twice, even though it appears twice, because we're just making a list of all the values included for our y's. That's the first question in number 1. Is the relation a function? So that a function is where every input goes to a unique output. So each of our x's has to go to only one y, which is what's happening here. 4 only goes to -2, 5 only goes to 0, 3 only goes to 2, and so on. What would make it not a function is if we added another column here and said that 4 also went to something else. That is where 1 input 4 would go to 2 outputs, and so that's not okay if we want a function. So what we actually have right here, yes, it is a function. And then it asks us what is the inverse of this, and so our inverse, if we remember, has to do with switching our x and y values. That's what an inverse means, that we take what was x and we put it where y is, and what was y we put it where x is. We do keep the columns consistent. We don't want to switch our numbers around left and right. So our first point would switch to -2, 4, and then 0, 5, and then 2, 3, and then 0, 10. And then it asks, is the inverse a function? So looking at this table of values, do we have every input going to a unique output? And this time the answer is no, because our zeros here go to different numbers, 5 and 10, which is a problem. Our inverse is not a function. So the original is, but the inverse is not. And you can have that happen the other way around, or they can both be inverses, or they can both not be inverses. It all depends on what information they give you or what graph they're giving you. 2 through 5 refer to this graph, and now that we're farther along in the semester, it might be that you know a lot more about this graph than you knew originally. So it asks us what is the domain, or to write the domain and range of the function in interval notation. Interval notation is the one with parentheses or brackets. It's my personal favorite, but and I think eventually, at least, it will probably be yours. If you're not used to it, though, it is a little tricky. So the domain is left and right. Is there anything stopping our graph from continuing on forever? And so because down here at the bottom, there are teeny tiny arrows, or just if a graph goes to the end of the grid, you assume it goes on forever. Because of that, even though it would take forever for us to go to the left or to the right because of how fast this is going down, we would in fact be able to keep going forever and ever. So our domain is all real numbers, or an interval notation, that's -infinity, positive infinity. Our range is that we stop here at this value. What I'm going to have to get real close to see if even that works. Are these going by twos? 1, 2, 3, 4, 5, 6, 7, 8, 9. I cannot read this. Yeah, I'm going to go with 9. I'm going to assume the scale is 1, so that's a 9. So our range is that our graph goes down forever, obviously, because it's like definitely pointing down. but it stops at 9, and there's no y values used on our graph after 9. But it does actually look like it touches at 9. These two humps on either side go up and touch 9 and come back down. And so we're going to say negative infinity, comma 9, and we're going to put a bracket around it. And some things to remember about interval notation is if a negative infinity is involved, it's always going to be on the left. If a positive infinity is involved, it's always going to be on the right, because our order, we want the left number to be the thing that is most negative, and we want the thing on the right to be the thing that's most positive. So especially on the range, I'll see people put 9 first and then negative infinity second, but we actually want to list them bottom to top, not top to bottom. And the other thing that's easy to forget is the brackets. Brackets mean equal to, parentheses mean not equal to. Infinities get parentheses, I assume, because of the idea that we can't ever actually be equal to negative infinity or positive infinity. They're concepts, not numbers. So just you'll always see parentheses around infinity and negative infinity. The end behavior of the function. And so there's a way that we write this that I'm going to start out here so I hopefully have room. As x goes to infinity, f of x goes to something, and as x goes to negative infinity, f of x goes to something. So we're trying to fill in the somethings. And when you look at this, we're not going to focus on the middle here where we've got this like down and up. We want to follow the very outside of our graph here on the left and say, as I go this way, as I go to the left, my graph is going down towards negative infinity. So that's the second one. As I'm going toward negative infinity for x, as I'm going to the left, then my y values are going down. Then as I go to the right toward positive infinity, my graph is going down that direction as well. So that means that as I go towards positive infinity, my f of x is going toward negative infinity. Number 4, what are the function's maximum and minimum values? So maximums occur at high points, like here, these maximums, which are at 9. And that's what we would call a global maximum, if we want to get particular, because, or an absolute. Those are two words for it, global or absolute maximum, because it really is the highest point in the graph. There is not an absolute or global minimum because our graph goes down forever, but there is what we call a local minimum here at, I'm going to say, negative 1.5. And we care about local minimums and local maximums to prepare us for calculus, and just in general, if our function is representing something, our local maximums and our local minimums are often helpful to the information that's going on. But what you're looking for to decide if it's a local max or local min is that your graph has either like a hill or a valley, but it's local if that's not also the highest or lowest point. So that's why it's local. Number 5, over what intervals is the function increasing and decreasing? The word interval suggests that we'll put this in interval notation. Increasing and decreasing is where we look from left to right and we say if it's going up, it's increasing. If it's going down, it's decreasing. But it's like we're reading a book from left to right. So we start down here and we say, if I try to travel to the right on this graph, I'm going to have to move my pin up. So I start off increasing until I get to this point right here. To write our intervals, we need x values, and we're going to have to approximate these. So I would say that, like, I'm going to call this like negative 1.2 or something like that. That our graph is increasing from negative infinity to negative 1.2. And then it starts decreasing from negative 1.2 to this down here. Let's call that a 0.5. Ideally, I would have made it really nice points, but it's hard to make everything in the problem a really nice point. So I knew something was going to have to get approximated, and I chose that this should have been negative, this minimum. I just realized, in case you were confused, negative 1.5, not positive 1.5. Okay, we are decreasing from here to here, and so we have to use these x values, and we're approximating it. And then from this 0.5 to up here, which is just a little bit past 3, let's say 3.1. So from 0.5 to 3.1, we're increasing again. And then at 3.1, it switches to decreasing, and it decreases for the whole rest of the time. I've used parentheses in all of this because there's actually some debate on how to do it. Technically, you're not wrong if you use brackets. But if we had a place somewhere on our graph where we had an asymptote or an open circle to show that it was not equal to, then we would have to put parentheses, not brackets. So I find it safer just to always put parentheses. And in my head, it makes sense because like at negative 1.2, where we're switching from increasing to decreasing, we're not really doing either. So to me, it doesn't make sense to put a bracket there anyway. But textbooks and mathematicians actually disagree, and the AP Calculus like test board or whatever, they accept either, and except for the cases of where things truly aren't equal at that point, and then you'd have to put parentheses. All right. 6. Find the inverse of f of x equals 5x plus 10. So remember that f of x is a fancy way of us saying y. And an inverse is where we switch x and y. And then what we're going to do is solve that. So x equals 5y plus 10. And then that means we need to subtract 10 and divide by 5, and then y will be by itself. And it may be that you don't even really need to show this work. In fact, I kind of hope that that's the case for most of us, that we can kind of keep track of that in our head at this point in our math career. But as a math teacher, I also like seeing work, so it's fine either way. So the way you represent an inverse is you write f and then you put a negative 1. And so a mathematician looking at that goes, oh yeah, you're talking about the inverse of f, in that tone of voice too. So here is our inverse for f. Number 7 is kind of a weird question, in my opinion. It's asking us to make a table of values using this absolute value function. And so when I do -2, I'm supposed to plug it in where x is. So they're showing us that here in the middle. And then if I work this out, I should have y. So -2 minus 4 is a -6. The absolute value makes that negative go away from 6 so that it's regular 6. And then we times by 3 and get 18. And then we're going to do the same thing. They just didn't set it up for us on the rest of these, so we'll have to set it up ourselves. So we're going to plug in 0 where this x is. 0 minus 4 is -4, switches to +4, times 3 is 12. Now I'm going to plug in a regular 2. And you do have to be careful because some of the assumptions you might make about what changes may not be correct because of order of operations. This being a +2 now instead of a -2 doesn't like switch the sign or something. It gives you a completely different number. 2 minus 4 is -2. We flip it now to a +2, and then we times it by 3 and we get 6. So there's our answer, 18, 12, and 6. Number 8. So this one, there's a couple different ways we could do it. Functions are inverses of each other if you plug them into each other and everything cancels and you get x. So on A, that's pretty easy to show. If I take f of x and I put the g of x where x is, so if I put that on top, but everything else remains the same, and then I think about how the negatives would cancel and the 5s would cancel, and it leaves me with x. And then if I do it the other way, if I take the g of x and write it down, but where x is, I put f of x. And then I think about how things cancel. The negatives cancel, the 5s cancel. I also get x. That is like the definition of things being inverses of each other. A fancy definition that when you plug them into each other, you end up with just x. The other way, and perhaps the easier way to do it, is to take one of them and actually try to solve for the inverse. So, for instance, on B, if I take y equals negative 3x minus 15, and I switch the x and the y, and we probably don't even have to do it all the way to see. If I add 15 over and then divide by negative 3, does this match this? No, it doesn't. So that's a no. That's the idea of what we're going to do here. If I have room. And so I'm going to go ahead and switch the x and the y. X equals negative 5y plus 25 over 2. So to solve this for y, we'd start by multiplying this 2 over. Then we'd subtract 25 and divide by negative 5. So subtract 25 and divide by negative 5. Now that's not what this looks like, but they don't have the negative on bottom. If we want to move the negative from the bottom to the top, it would make this a negative 2x and a positive 25. And that does match this, so that is a yes. A tip for finding inverses is you typically will see the same numbers used, but kind of rearranged. So the fact they both had 25s, they both had 2s, they both had 5s. It's a good indication. So like my gut instinct on D is no, because why does this one have a 20 and the other one doesn't? And if all you're looking for is a gut instinct reason to pick an answer, there you go. But hopefully you're interested in more than that. You'd have to multiply by 3 and then add 20 and then divide by negative 4. And there's no way that that ends up being g of x. So nope, those aren't inverses. Let's look at the next question. The figure below shows a transformation of y equals the absolute value of x. Refer to the figure for numbers 9 and 10. So write the function that is represented on the graph. This graph has been shifted to the left 3. So that's something we're going to have to incorporate. And it also looks to me like there is a stretch, because a normal absolute value graph would be here at up 1 and over 1 each direction, but instead it's up 2 and over 1. So this has been vertically stretched by 2, or you could also think of it like you horizontally, sorry, not vertically shrunk, vertically stretched by 2 or horizontally shrunk by a half. I personally prefer to write things as vertical stretches versus horizontal things. So I personally would write this as y equals the 2 that it's being stretched by would go on the outside, and then left 3 means we use the super secret opposite society, and it's really a plus 3. Anything that happens to x left and right is going to be in sign, but is the opposite of what it would normally be. The other answer, though, you could, because it's absolute value, and this is a uniquely absolute value thing, you actually can put the 2 inside. But what that changes is that we'd actually need our x plus 3 to be in parentheses to show that shift to the left of 3, which is another reason why I personally really like to just think of it as a vertical stretch instead of a horizontal shrink. Write the domain and range in set notation. Set notation is the fancy one with the squiggly brackets. So you put squiggly brackets and you do x and you do a line. So this is our domain, is all x's where x is a real number. Like our domain is from negative infinity to positive infinity. So we could write that with inequalities, or we could write in here where x is a real number, and that would work. Our range is not negative infinity to positive infinity because we have this low point here where that's where our graph starts because we want to go bottom to top. So that y value is 0. We want to use y's here instead of x's. Oh, I'm not going to use a bracket because that's the wrong form. Close one. So we're saying that y has to be greater than or equal to 0. That's one way to write it. If you were to put 0 is less than or equal to y is less than infinity, that's also still technically correct. It's just you've written more than you had to, but that doesn't mean that it's wrong to do that. But that is how we do set notation. That's how we do domain and range on an absolute value function. Our absolute value function could, of course, open down instead if there's a negative in front, and that would mean we'd have like negative infinity to something instead of something positive infinity. We've got to graph this function on number 11. So here's what is happening. Here's what is happening. The negative at the very front flips it down. And the 1/3 is a vertical shrink. Absolute values have the unique property that you can basically think of negative 1/3 as a slope for 1/2 of your graph. The x minus 2 means that we're going to the right 2 because it's the opposite of negative 2. And the 3 on the outside is up 3. That's a lot of things to do. So the first thing I would do is put our bottom or top point, which is right 2, up 3. Call this our vertex. Just like on a parabola, that's our high point or our low point. Since it's flipped down, that's our high point. When I draw my next points, what I want to do is it's actually easiest to think of this slope of 1/3 that I want to do down 1 over 3 each direction. Or the other thing to think about is that normally our graph would be down 1 over 1. We want it to only go 1/3 of that distance, which is like right here. That's the other way to think about vertical stretches and shrinks, is multiplying whatever our normal number would be by that vertical stretch or shrink. So there's our graph. It looks great. Best graph ever. Oh, we've got some i's here, 12 through 14, adding, subtracting, and multiplying. So the thing to remember with i's is you can treat them like an x, except for the property where if you end up with an I squared equals -1. Now, I've had some people recently trying to change the i's to -1s, but that's not how it works, right? I is the square root of -1. So we want to leave i's that are regular i's alone, but if it's I squared, then that's when we want to change it to -1 without the square root. So that should only happen to us on the multiplication, 14. So on 12, we're adding these together. So 3 plus 4 is 7, and 11i minus 12i is -i. And that's all we do there, 7 minus I. When we subtract, we have to remember to subtract. 10 minus 13 is -3. Very few people forget that part, but now if I want to do -7i and I want to subtract -2i, that's really adding 2i. So -7i plus 2i is -5i. So that's my answer on 13. And then 14, I'm going to FOIL or use the distributive property, depending on which way you prefer to think of it. They're the exact same steps. 3 times 2 is 6. 3 times -8i is -24i. 8i times 2 is 16i. And 8i times -8i is -64i squared. So our like terms in the middle here we can add together, and we also want to change this to a -1, which makes it go away, and it just changes this to a positive instead of a negative. So then we end up with other like terms. We have 6 plus 64 is 70. -24i plus 16i is -8i. So there's our answer to that. Number 15, there are 2 hiking trails at Parkham Park. One trail can be modeled by the equation y equals negative 2x plus 2. The second trail can be modeled by negative blah, blah, blah. Determine if each of the following is a point where the paths will cross. Choose yes or no. So we could solve this for the 2 answers. And so if we wanted to do that, since they're both y equals, the easiest thing to do would be to put them equal to each other, like this. The other way to do it, which I think is actually faster or easier, is to just plug in these points to both equations to see which ones work. Like if I plug in a 2 for this x, negative 4, or negative 2 times 2 is negative 4, plus 2 is negative 2, that's not 0. So this is already a no. It has to work for both of them in order for it to be a point where the paths cross. So we plug in 0, and that is 0 plus 2, which is 2. So this one works for the first one. Let's check the second one. Plug in 0 and get negative 1 squared, which is 1, and then we make that negative. So negative 1. Negative 1 plus 3 is 2. That one's a yes. Then we look at C, 4 and negative 6. I might need to write something down at this point. Negative 2 times 4 plus 2. Negative 8 plus 2 is negative 6. Yes, that's right. And then negative 4 minus 1 squared plus 3. So this is 3 squared, which is 9, and then we make it negative because of the negative in front. So negative 9 plus 3 is negative 6, so that's a yes. Chances are this is going to be a no since it's the flip of this one. Hopefully we'll see that pretty quickly here. 12 plus 2 is 14, so that's a no. But you could just solve it. Or even you could graph the two of them in the same graph and get an idea of about where they're crossing from the graph, and that would be enough to also decide which ones are yes and which ones are no. Number 16, solve the system of equations to find the values of x, y, and z. So when we're doing this, my preferred method is elimination. And what I do is I look at the whole picture at all of the x's, all of the y's, and all of the z's, and I say, what's the easiest thing to eliminate twice? So I'm kind of inclined to pick z because I can add the first and the third equations together right off the bat, and they'll eliminate z. And then to do it a second time, I just need to multiply the middle equation by either 5 or negative 5, depending on which one I want to put it together with. Now, this may not be enough room for this work, and so you're welcome to do it on a different piece of paper. I'm going to see what I can make happen. So I want to take the first equation and the third equation. I want to add them together. So that cancels that out. And then 4x plus 10y equals negative 12. Then I'm going to do the middle equation times 5 and then use the third equation. So negative 15x minus 15y plus 5z equals 35. And then 2x plus 6y minus 5z equals 4. So negative 15x plus 2x is negative 13x. Negative 15y plus 6y is minus 9y. These problems are tricky because like any errors along the way, and I could have already made one and not even know, any errors along the way here are going to make this not work. And that's a frustrating situation. Now I put these two together to get our x's or our y's to cancel out, and trying to decide if I would rather not multiply by 13 personally. So I guess I'm going to multiply to get 90. So that means this times 9 and this times 10. So this is a 9 over here, but I realized I might have been going off of the screen capture. So there we go. All right, so 9 times 4 is 36x plus, and then we got 90y, and then we've got negative 108, and then negative 130x, and then negative 90y, and then 390. We're getting some big numbers here. This is negative 94x, and this is $282, and hopefully this divides in 3 times. It does. So x is negative 3. And then I plug in the negative 3 to one of these equations that have x and y. So I'm going to pick this one because it has the smallest numbers. So 4 times negative 3 plus 10y equals negative 12. Negative 12 plus 10y equals negative 12. So I add 12y over, it cancels and gives me 0. And I divide by 10 and I get 0. And then I plug negative 3 and 0 in to any of the equations at the beginning or these equations down here and get z. So 2 times negative 3 plus 4 times 0 plus 5z equals negative 16. Negative 6 plus 0 plus 5z equals negative 16. So I add the 6 over, get negative 10. So z equals negative 2. Now, since I got nice numbers, I feel like there's a good chance that I did this right. Oops. Okay. Since I got nice numbers, there's a good chance that I did this right. But the best way to find out is to actually plug these in for x, y, and z and see if it works out. So negative 3 here, 0 here, negative 2 here. That's negative 6 minus 10 is negative 16. I have to do that for all of them. So the next one would be 9 minus 2 is 7. That's right. Negative 6 plus 10 is 4. That's right. So yes, this is the correct answer. Negative 3, 0, negative 2. Most of the time, if you mess something up, you end up getting fractions. And it's not that you can't get fractions on these, just typically we're nicer than that as math teachers. So a fraction is a decent indicator that maybe you did something wrong. But sometimes it can be hard to tell if you get whole numbers. It's hard to tell where you might have gone wrong. 17. The graph of a quadratic function has a vertex at negative 2 comma 3 and opens upward. Choose true or false for each statement. So a quadratic function is a parabola. And so all we really know about it right now is its vertex is at negative 2, 3, which is here, and it opens upward. We don't know if it's vertically stretched or horizontally shrunk or like we know that it's shifted, but we don't know, and we know it's not reflected. We don't know how fast it's going up. So let's see what our choices are here. A, part of the graph is in quadrant 1. Well, not the part that I've drawn, but if it continues going up and to the right, eventually, yes, it will cross over into quadrant 1. So yes, it is. The point negative 2 comma negative 5 could be on the graph. Where is negative 2, negative 5? Down here. Is there any way for this to be on the graph? No. Part of the graph is in quadrant 4. That's this one down here. And because it's pointing up and is higher than quadrant 3 and 4, there's no way for it to be in either of those quadrants. So false, it is not in quadrant 4. And the point negative 1, 4. So negative 1, 4 is right here. We don't know for sure, but it could be on the graph, so true. It all depends on if there's a stretch or a shrink or not. 19, use the binomial theorem to expand n plus 5 to the 6th power. So the binomial theorem is where we notice the pattern for expanding these, where the n's and the m's, we start off with an n to the 6th, and then we have an n to the 5th, but then we gain an m to the 1st. We've got n to the 4th, and then our m goes up. So as our n's are going down, our m's are going up, and all along the way, our exponents are going to add together to get 6. And so then we've got n squared and an m to the fourth, a regular n, an m to the fifth, and then an m to the sixth. And then what we need to add in here are coefficients for this, and those coefficients, one way to get them is Pascal's triangle. We need the 6th row, or the row that has 6's on either side, right next to our 1's, which I don't have memorized, and I don't want to scroll up to the triangle at the top. So here is our 6th row, here's our coefficient. So we'd have 1 into the 6 plus 6 into the 5th m plus 15 into the 4th m squared plus 20 n cubed m cubed, and then plus 15 n squared m to the 4th. Then pull, that kind of looks like I'm adding on to the 4 there. Okay, and then plus 6, and then plus 1. So here is our expansion. Easy peasy. What makes it pretty fast and pretty easy is when you don't have coefficients for your 2 letters here. If you do end up with coefficients, then you have to also use the exponent for n or m with that coefficient, and then multiply it with the coefficient that we get from Pascal's triangle. But you know, that's not what happened here. Oh, okay. Number 19, sketch the graph of the function. So here's the information that we can know without doing a ton of work. We can know that we've got a 0 at 0 because of the negative 4x. We've got a 0 at 1, so the x minus 1. And we've got a 0 at negative 2. Actually, we've got that twice, and that is what we call multiplicity. So at 0, we know that the graph goes through because we get that answer once. At 1, we know it goes through, but at negative 2, it actually bounces. I don't have a good way of writing that on my graph right now. The other thing we can think about is there's 4 x's essentially, x, and then x squared. So this is a 4th degree polynomial. And so we can think about the end behavior of all even polynomials. We can also look at this negative in front and say, oh, that means that my graph is flipped to be the opposite of a positive graph. So 4th degree is like a parabola, and negative means that it would be opening down. So what happens though is as we get to 4th and 6th and so on degrees is that there can be squiggles in the middle. And so we've got squiggles happening here, but we know the only places it crosses are at 0, 1, and negative 2, and that at negative 2 it's supposed to bounce and not actually go through. So I'm going to start here on the right. I know that it goes down to the right. I know it has to go up and come back down and go through at 0. I know it has to go down and come back up and bounce at negative 2, and then it has to go back down. Now, what's not accurate about this graph is where it is getting up to or down to. For that, I would need to either graph it on my calculator or something. Plug-in points. There are ways you could make a more accurate graph than that, but if it says sketch, it's not looking for perfectly accurate, which is nice. 20. We're going to add this polynomial together, and so we're looking for like terms. 3x to the 4th and negative 8x to the 4th is negative 5x to the 4th. So that's those. The x cubed add to get negative 5x cubed. And the x squareds add to get 14. And the x's add to get negative 1x. And 7 and negative 2 add to get 5. So that is adding. Our subtraction problem here is a little bit more complicated. Does each expression equal 3x to the 4th plus x cubed minus 7x squared minus 11x when simplified? Yes or no? All right, so we've got 3x cubed minus 2x cubed is a single x cubed. That works. And that's these two. We've got negative 11x, and it's not going with anything else, so that works. Negative 7x squared doesn't have anything else to go with, so that works. Negative x to the fifth minus negative x to the fifth, so that's really plus x to the fifth. Those actually cancel out, which is good. And then we've just got this 3x to the fourth, but we're subtracting the 3x to the fourth, so that means that should be a negative 3x to the fourth. So that's a no. And notice how subtle the difference was there. So you want to definitely be paying attention. Here on B, 3x to the fourth is right here, and so it doesn't have a negative in front, so that's fine. There's not anything else to add to it or subtract from it. 4x cubed minus negative x cubed, so 4x cubed plus x cubed is 5x cubed, which doesn't work, so this is also a no. It's more likely that we'd get a yes and a no, but things happen. So probably an error on my part. I feel like I got the exponents off when I wrote this. Or maybe I did it on purpose. I totally did it on purpose just to try to trick you. They're both no, which is okay. It's totally fine. All right, 22. Draw the graph of the function shown below. Draw the graph if the function shown below is translated 3 units left and 2 units down. Draw and label the reference points on the curve that you draw. So it's talking about how I have dots pointed out for you. We're going to make sure to draw those dots as well. So if we take this graph and we translate it 3 units to the left and 2 units down, then each point needs to go 3 left and 2 down. So that's here. And then this is 1, 2, 3, 1, 2. That is here. And then 1, 2, 3, 1, 2. And so then we want to make this look like they did as much as possible. It says draw and label. I mean, we could call this A and this A and this B and this B, C and this C, or maybe writing out the coordinates would be better. I don't know, I kind of like this labeling system, personally. But if we're thinking of like our good old geometry days, we'd put an apostrophe here to show that it's the new A, B, and C and not the old A, B, and C. 23, does each product result in this thing? So x squared times x is x cubed. X squared times y is x squared. Negative y squared times x is negative xy squared. Negative y squared times y is negative y cubed. So we've got a yes. B is more complicated. So you have to actually multiply out x plus y times x plus y and then times it by x minus y. So that's x squared. And then we'd get xy and xy twice. So that's plus 2xy. And then y squared. We're multiplying that by x minus y. It actually probably would have been faster to do these two together and then do the other two. But oh well. We get x cubed plus 2x squared y plus x y squared, and then minus x squared y minus 2xy cubed minus y cubed. So we've got some like terms here. These two make 1x squared y, and these two make a negative. I don't think that was supposed to be a cube. That was supposed to be a squared. So then these two make a negative 1 xy squared. So that does actually also equal. So maybe on the other one I did intend them to both be no, because these are both yes, and I remember intending them to both be yes. So you never know. You never know. Okay. Choose true or false for each statement about factoring. We've got this polynomial, and it's asking us how we can factor it. So can you factor out the greatest monomial factor? I can. It looks like they have a 2x squared in common that we could factor out, so that's a true. Can you factor by grouping? Now, the best way to know if I've said this before in my class, and it's like, wow, that sounds really dumb, but it's exactly what I'm trying to say. The best way to decide if you can factor by grouping is to try to factor by grouping and see if it works. So you group these two together, you can take out a 2x to the fifth, and that leaves us with x squared plus 5. And you say, what do these have in common? 16. Nope, they've got a 32 in common, a negative 32x squared, which gives us x plus 5. Well, that's really close, but that does not work, x squared and x, so that's a false. You can factor using a perfect square trinomial pattern. Well, this is not a trinomial, so no, we can't. That's false. You can factor using the difference of two squares pattern. So that's the pattern. If you have like a squared minus 9, that you can factor that into a plus 3 and a minus 3. Maybe if this worked out a little differently over here, if we had like an x squared minus 25, then yes, we could. But that's not what happens, so no, we can't. The only thing actually that we could do on this was factor out the greatest common factor. Although, again, I feel like maybe I intended for factoring by grouping to work, but I can't actually remember. It's been too long since I made this. For 25 through 27, factor the polynomial or identify it as irreducible. Irreducible is a fancy word for not factorable. So if you have 4 terms, then you're probably factoring by grouping. Check for a greatest common factor first. There's not one. So we want to group these and group these, just like what I did up above. So I want to take out the 2x to the fourth from the first group, and that leaves me with x plus 4. And then I want to take out the negative 3x squared, and that leaves me with x plus 4. So I can factor this one by grouping. It's x plus 4, which is what they have in common. Oh, I could have taken out an x squared at the beginning because these both have x squareds. So I can take that out now instead. And then that leaves me with 2x squared minus 3. That doesn't factor anymore because I can't square root the 2 or the 3. So this is my answer. So if that was confusing, I would have ended up with 2x to the fourth minus 3x squared in one of the parentheses, but these have something in common you can take out. So that's why I took the x squared out and put it at the beginning, and then had the 2x squared minus 3. So 26 is a trinomial. So our hope is that there's something that multiplies together to get negative 28 that adds to get negative 3. So I'm going to go 7 and 4. One of them needs to be negative, and it needs to subtract so that I get a negative number. And so that's negative 7 and plus 4. And since most recently we've been factoring and then solving, please notice that all it asks you to do is to factor and not to also solve. 27, we've got a sum of 2 cubes, and so there's a formula, sort of a thing, like a pattern that we memorize for this, that this equals the cube root of each of these times the first one, this first thing squared, minus the 2 things multiplied together, plus the last thing squared. And so a and b are the cube roots of these two numbers. So the cube root of 8x cubed is 2x, and the cube root of 27y cubed is 3y. And then when we put that here, 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 and here, we've got to square or multiply or things like that. For instance, 2x when I square it is 4x squared. A times b is 2x times 3y, which is 6xy. And our formula has a negative there, because if I multiply this all out, I need things to be able to cancel to get 8x cubed plus 27y cubed. And without a minus sign, nothing would cancel. Put 3y right here, so that's 9y squared. And this is my answer. Moving right along. 28. Is each binomial a factor of this long polynomial? So if it's a factor, then if I use synthetic division, with the thing that would make this 0, then I should end up with a 0 at the end. So I'm going to do synthetic division with 1 and then with 4. So drop the 1, multiply, add, multiply, add, multiply, add, multiply. This one does work because I get 0 for my remainder. Let's try it with 4. There are other ways you could do this, but if you're pretty fast with synthetic division, then I would argue this is probably the fastest way. Well, there's definitely no way that's going to work out. So double check your math or my math. But it does not look like this works. So that's a no. Okay, 29. Describe each change involved in the transformation resulting in the graph of g of x equals negative 2x cubed plus 4 from the original graph of f of x equals x cubed. So we've got a negative, we've got a 2, and we've got a 4. The negative makes this reflect across the x-axis. And I know it's the x-axis because it's outside. When you make the inside negative, essentially you're making x negative, it flips it over y. But when we make the outside negative, it flips it over x. So reflect over x. That's the negative. The 2 is on the inside, and so that means it is you have to flip it over and think of it like 1/2, and so that means it's a horizontal shrink of 1/2. And then the plus 4 on the outside is a shift up of 4. And so these are all rules that we went over when we did absolute value. We did it actually in chapter 1, and we used parabolas for that. And then we did it with cubic functions, and that would have been, I think, I said chapter, I meant module. In module 5 is cubic functions. So, and it's the same rules for everything, no matter the function. And you're looking at what's inside or what's outside and all of that jazz. 30, sketch the graph. This is actually a similar method of what we would want to do on the one we sketched earlier. We've got zeros here of 0, 1, and negative 4. They all have a multiplicity of 1, so we're actually going to go through our graph for all of these. And then if we think about x times x times x is a cubic function, it's a positive x in front, so it's a positive cubic function. Positive cubic functions are like positive cubic functions or positive slope lines where we go up to the right and down to the left. So I need to go this way and this way, and I need to squiggle in between. And if we want to be more accurate with how we squiggle in the middle, wow, sorry, talking is hard. If we want to be more accurate about that, we would graph it on our calculator or plug in values in between these points. So over here, between 0 and 1, we'd have to plug in a fraction, which would be no fun to actually see how far down it goes. But on the other side, you could plug in negative 2 to see kind of approximately how high it gets. Negative 2 doesn't have to be where the maximum is between there, but it could be. But it'd give you an idea of how tall that is. And I did not actually I wanted to not think about the scale for the y's because that makes it way easier to think about this. So it may be that the 4, the 2, the negative 2, and the negative 4 wouldn't work if you actually graph this. So you could mark out those numbers and change them if you wanted to, or you can just ignore them like I did. 31. Just giving you time to read it while I yawn. Write a quartic function in intercept, also known as factored form. In other words, we are going to use the zeros, and we're not going to multiply this out because that would be more work than we need to do. So it tells us our x-intercepts are integers, which means that if we can figure out where it's going through the x-axis, it's not secretly like a little bit off of the whole number. And then our constant factor, that would be at the beginning in front of our parentheses, or if we have an x in front of our x, is either going to be a 1 or a negative 1. Okay, so we've got a negative 2 here. We've got a 1 here. We've got a 3 here. So in factored form, we put parentheses around those and we change their signs. So we'd have x plus 2, we'd have x minus 1, and we'd have x minus 3. But wait, this is supposed to be quartic, and this is only 3 x's because it bounces right here, which implies that there is a squared, because we need an even multiplicity. The other thing we need to account for here is that this is going down both directions, which implies that this is a negative leading coefficient, and to make that happen, we just need to put a negative at the very front. I was about to put negative x, which would actually have been really bad, and now it kind of looks like a 1, but I just want to actually get rid of it and say all we need to put is a negative, that this is a negative of the positive version of this, which would open up instead of down, and then put some sort of a function thing at the front. F of x equals negative x plus 2 squared, x minus 1, x minus 3. The order doesn't matter, but it does matter. It does matter that you put the squared with the x plus 2, because that's the one that is bouncing, not the other ones. 32. So this is where we get into module 7. Find the quotient and remainder of. If you notice that this is something you can use synthetic division on, you should definitely do synthetic division, which is easier. You want to make sure that you don't need any placeholders, which we don't. We want to do some synthetic division. And because it's just a division problem in general, and it even mentions a remainder, we shouldn't feel bad if we end up with a remainder. To write our answer, it started as x cubed, so we want to start with x squared. 10x squared plus 5x plus 3 plus our remainder is 2, so they do 2 over what we divided by, which is x minus 2. And that's our answer. According to the fundamental theorem of algebra, how many solutions should the following polynomial equation have? The fundamental theorem of algebra is what relates the biggest exponent in our polynomial with how many solutions we have. So the fact that this biggest exponent is a 5 means there should be 5 solutions. It doesn't tell us what kind of solutions they are, but it tells us that there are 5 of them. I guess it tells us that they're complex, because everything is complex. But it doesn't tell us how many are real, how many are rational, how many are imaginary. Just know that there's 5. 34. List all the possible rational zeros of the polynomial f of x equals blah, blah, blah. So that's where we take the factors of this over the factors of this and make a list. So the factors of 18, 1, 2, 3, 6, 9, and 18 over the factors of 3, and they all can be positives and negatives. So I'm going to put all of these over 1, and I'm going to put all of them over 3. I'm not going to repeat the ones that are the same in both. Like some of them on the second way through are going to cancel to be the first set of things we got. So like 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, 6 over 1 is 6, and 9, and then 18. But then we've got 1 over 3, and then 2 over 3. Oh, a bunch cancel out. I'm running out of room. 3 over 3 is 1. 6 over 3 is 2. We've already got those. 9 over 3 is 3. And 18 over 3 is 6. So, phew. These are all the possible rational zeros. Something that some people have been confused about recently is if I ask you how many zeros are there, I'd look at the degree and say, oh, there's 3 zeros. That has nothing to do with our list of possible rational zeros. If I have to try to solve this and get the rational zeros, these are the things I should try first. If I don't have a graphing calculator to just show me the graph. So this is what I should try first, but maybe 3 of them are right, or maybe only 1 of them is right, because the other ones can be non-rational zeros. So don't get mixed up there and think, oh, I should only have 3 possible rational zeros because there's only 3 zeros. The word possible means like what could be a rational zero. And this is a long list, but it's shorter than the list of all whole numbers. All right, 35, which is a list of all of the roots of x cubed minus 4x squared plus 2x minus 8 equals 0. So let's check to see if we can factor this by grouping. Because if we can't, then we're going to have to use our roots theorem to get a list of possible rational roots, and then we would have to do a bunch of synthetic division. But this does work. This is x minus 4 times x squared plus 2. And so we're going to set each of these equal to 0. I get a 4 for this. And so it can't be a or d. But then when I solve x squared plus 2 equals 0, I would have to subtract the 2 over and square root both sides and get x equals positive and negative I square roots of 2. So that is B.
$36. We have a polynomial here. It tells us that it has zeros of 0, 2, and 3 plus I, and it asks what is its fourth root. And so this is like a concept question, because what we need to know is that roots come in complex conjugate pairs, and so the 0 and the 2, we wouldn't get any more information out of that, but the 3 plus I means that 3 minus I also has to be a 0, and so we're going to pick that out of the lineup here. And that's only true for our numbers with square roots or imaginary numbers. Anything else can just be a single thing. Like 0, of course, doesn't have a negative to have an opposite of, but 2, like it being a 0 of 2 does not mean that negative 2 has to be a 0 as well. That's not a rule. It has to involve an I or a square root. 37. Write a polynomial function of least degree that has real coefficients, the following zeros, and a leading coefficient of 1. Now, a lot of this information is just to ensure that we all come up with the same answer, like the leading coefficient of 1. At the end of this, I could multiply this by 7, and I would get a different leading I would have a different leading coefficient, but still would have something that has these 3 zeros. And there's other things that we could mess with in a similar way. It's saying, hey, just find the simplest answer, essentially. So we make these into factors. So the minus 1 becomes x plus 1. The negative square root of 3 becomes x plus the square root of 3, but we have to remember that square roots come in pairs, so I also need the opposite. And then the 2i, those come in pairs as well. And I mean, every time we've solved, like with the quadratic equation, we should have seen this happening, or solving by square roots when we put the plus and minus, like this should be happening the whole time. It's just that maybe we didn't notice that it was an actual rule that these come in pairs, a plus and a minus. All right, so I'm going to multiply these two together because the square roots will cancel, and these two together because the i's will cancel, and then we'll have to do a couple more multiplications. This is as long as this problem can get. Well, technically not. I mean, I'm not going to give you something like 2 plus I, which would then have 2 minus I and would be harder to multiply out. That's not a plan, and so that would make it longer, but not going to happen. So when I FOIL this or distribute this, the x and the x make x squared. The x times negative square root of 3 and the square root of 3 times x cancel each other out, and then square root of 3 times negative square root of 3 is a negative 3, because you multiply the 3 together and get 9, but then you square root the 9 and get 3. Then something similar but not the exact same happens with these. X times x is x squared. The outer and inner terms cancel because they're both 2ix, but one's a negative and one's a positive. When I do negative 2i times positive 2i, I get negative 4i squared, because I multiply the numbers 2 and 2 and get 4. I multiply the i's and get I squared. And then the I squared, I'm going to make that go away, and it changes the sign to a plus 4 instead of a minus 4. And so now there's not a best way to do this. We just need to do 2 of them multiplied together and then multiply the third one in after. So if I do the first two together, x times x squared is x cubed. And then x times -3 is -3x. 1 times x squared is x squared. 1 times -3 is -3. Keep in mind that this is my first time doing this problem, and I'm a human being that can make mistakes. And so if you notice a mistake, feel free to let me know, and maybe I'll change it. I don't know. As far as YouTube goes, like, I'd have to re-upload the video. Or put it in the description or something. Give you a shout out if you find a mistake. X cubed times 4, especially because I just talked while writing that, there's a good chance I did something wrong. So x to the 5th minus 3x cubed. Okay, that looks fine. So now timesing by 4, I'm writing it underneath the like terms that I have. So -3x times 4, although that's the only like terms I have. Nope, this is like terms. X squared times 4 is 4x squared, and then minus 12. So when I add these together and I write this as a polynomial, I can use whatever letter I want to here, but earlier in the review they've been using p of x for polynomial of x. We've got x to the 5th plus x to the 4th if I want to put it in standard form, plus x cubed plus x squared minus 12x minus 12. And it does have a leading coefficient of 1. So there you go. And all real coefficients. Now the next part of this says that you're required to complete one of the 4 word problems as a part of your final exam grade. But if you were to successfully do more than one, you could get extra credit. And so these are word problems, and they're going to use some of the different things that we've done. The tricky thing is going to be knowing what they're asking you to do. So this first one, a rocket is launched into the air. Its height in feet after t seconds can be modeled by the function given here. How long would it take the rocket to reach a height of 100 feet? So think about which letter, H or T, is the height, and so that would be H. So where H of T is, we're going to put 100, and that equals 116t minus 16t squared. And so to solve this, I want to probably get everything on one side and either try to factor or quadratic formula. Hopefully it factors, but it also might take some effort for you to know what it factors by. We also either later or right now can say, oh, I can divide all these by 4 and make this a little bit easier. 4 into 11 goes twice with 3 left over. So we've got this, and we can move that onto one side. So 4t squared minus 29t plus 25 equals 0. So if I want to factor this, I would have to do 4 times 25, which is 100, and say what multiplies to get 100 and adds to get negative 29. And so that's negative 25 and negative 4. I just kind of blinked. X minus 25, x minus 4. And then I divide them both by this front number 4. This is a trick for how to factor without having to guess and check. So this 4 would have to move in front of x because it doesn't simplify away. This 4 does, though. This would turn into x minus 1. And so that means that x equals 25 fourths and x equals 1. So let's think about what it asks us. How long? I switched to x instead of t. That was silly. These should all be t's. So how long would it take the rocket to reach a height of 100 feet? So what's happening is we've got a parabola here. And so it's reaching 100 feet here at 1 and here at 25 over 4. So I would say that both of these are technically our answer. So it will reach 100 feet at 1 second and 25 fourths, which is what? 6 1/4, so 6.25, 6.25 seconds. And so the reason I'm writing out my answer is this is a typical thing you should think. They gave us the problem in words, so we should answer them in words. With units and I would argue that in this case, since it's a nice decimal at least, it makes more sense to give them the decimal. Like if you were talking to some rocket scientists, I feel like maybe they'd be more interested in 6.25 than 25/4 as an answer. But you'd have to ask a rocket scientist to be sure of that. Number 2, a paper airplane is thrown up into the air from the top of a 60-foot building. So top of a 60-foot building, there's a person up here throwing a paper airplane, which is not something that's a good idea, so don't do that. The airplane follows a path with height h above the ground at time t. So kind of a similar formula to what we had before. You'll notice that they both had negative 16s, which has to do with gravity. Spoiler alert for physics if you haven't taken it yet. Function models the airplane's path. How long does it take the airplane to reach its maximum height? So what's happening is that it actually, you're throwing it up, and so then gravity takes over at some point and makes it start to fall back down. So what is the maximum height? And that's also known as the vertex of our parabola. So how do we find the vertex of this parabola? There's a few different ways to find it. One way to find it is to put our equation in vertex form by completing the square. That's an option. The other way is there's a formula to find the vertex that's negative b over 2a, and that's the easier thing to do. If you take this and label it a, b, and c exactly like what we do with a quadratic formula, then you put negative 16 over 2 times negative 16, and then that gives you 1/2. So that means that it takes a ½ second for the airplane to reach its maximum height, which sounds about right. So the airplane will reach its maximum height at 0.5 seconds. And you don't have to change it to a decimal. Either a half or 0.5, whichever one works for you works for me. But that's the idea of finding the vertex. Number 3, a television has an area of that many pixels and a width of that many pixels. Find the length of the television when the width is 4,000 pixels. And then there's a nice sentence that says, I did not actually research how many pixels televisions these days have, so this is most likely not something that actually makes sense. As far as real televisions go, I thought it was more important to make the numbers work out nicely and to not have to spend forever making the problem. And so this is what we've got. So find the length of the television when the width is 4,000 pixels. So they give us the area and the width. Here's our area. And they give us the width. Although they actually give it to us. I don't need these parentheses here. That was silly. They also tell us, though, that, hey, this is 4,000 pixels. So there's a couple different ways we could go about this. We could divide the area and the width, and that would give us length, and then use the 4,000 somehow. Or we could go ahead and say, well, if the width is 4,000 and the width is x minus 2,000, then if I add 2,000 to both sides, I will know what x is. We can see if that helps us out here at all. X equals 6,000. So that would mean that our area is 6,000 squared minus 4 million, which is hopefully something that works out. And then once we know what the area is, if we do the area divided by the width, then we'll know what the length is. So, so we just need to do 6,000 squared minus 4 million. So 6,000 times 6,000 is 36 with 6 zeros. And so that subtracts to be 32 million. And so then our area is 32 million pixels. Our width is 4,000 pixels. So we're dividing these to get our length, which is sorry, I had to sneeze. 32,000 divided by 4 is 8,000. And so, like I said, I don't know how reasonable it is to have a TV that's 8,000 by 4,000 pixels. I really don't care, because isn't it nice that we got such nice answers? Isn't that pretty awesome? All right, finally, this is like a pretty classic problem that you see at multiple levels of math even. But because of our level of math, we can kind of do different things and go farther with it and that sort of thing. So to make an open rectangular box from this 10-inch by 14-inch sheet of cardboard, we cut out squares with side length x out of each corner so that then we can fold up the sides. It'll be an open rectangular box because there won't be a lid unless we make a separate lid. So we want to determine the values of x that result in a volume of at least 96 inches cubed. Oh, actually, it says what inequality do you need to solve? We don't even need to find out what x is. We just need to write the inequality, if I'm reading that right. I feel like I'm reading that right. So what we need to think about is that volume is length times width times height. They're telling us that the height is x because when I fold up this side, it has a side that becomes x. You have to be able to kind of imagine this 3D, that whenever I make my box by folding up the sides, this right here is the x, because that's the place that is missing here. And so then we need to think about the two sides that we've got going on in terms of because of the fact that our sides are not going to be 10 and 14 because we're taking out this x on either side. So this middle part minus these two x's the middle part here is the 10 minus our two x's that we cut out. So our width is 10 minus two x's. Our length, the same thing. The total length is 14, but we have to take away two x lengths. So that's 14 minus 2x. And then our height is just x. We want this to be at least 96 inches cubed. So we want this to be greater than or equal to 96 because that's what at least means. And it always helps me to think about money and to think if my dad says he's going to give me at least $96, then he's going to give me greater than or equal to $96. And I'm hoping for greater than, but I do have to remember that it could be equal to. So this is the inequality we need to solve. It doesn't ask us to solve though. So we're going to call that good. That's the whole review. So happy studying.